10.7 Lagrange error bound and accuracy. At this point in our study of calculus, we have explored many methods to approximate values for a function. We could simply estimate by looking at a graph, or we could use the tangent line approximations that we've learned, or we could use Euler's method, and now we have Taylor polynomials also as a way to approximate values of a function. So, remainder, error, and accuracy of a Taylor polynomial. When we use Taylor polynomial approximations, it would be a good idea to know how accurate they are to the exact values of an infinite series. The function value by the Taylor polynomial can be defined by the concept of a remainder, defined as f of x is equal to the polynomial sub n of x plus the remainder sub n of x. So the exact value is equal to the approximate value plus the remainder. So the absolute value of the remainder, r sub n of x, is called the error. So the error is the absolute value of the remainder sub n of x, which is our f of x minus our p sub n of x. And basically, we're going to take into, it'll be like, n might be 3, where we're going to use 3 of the values of our series. The first 3 values, or we might use the first 5 values. But the remainder is going to be that 6th value, okay? Or that, if we use 3, that 4th value. It's always going to be equivalent to the next value. So graphically, when we use a Taylor polynomial, t sub n of x, centered at x equals c to approximate a function f of x at a value x equals a near the center, we can say the following. If the function, which since we're finding the x equals a, so our function at a would be equivalent to the polynomial approximation would be our Taylor polynomial sub n of a, and then plus our remainder sub n of a. Then the remainder, r sub n of a, is equal to my function's value minus the polynomial approximation. And all you're doing is just, rearranging those because your remainder is going to be equivalent to what is left over after, basically your error, your exact minus approximate. So let's go ahead and draw a picture of this. So we have a function f of x, and we are going to center our Taylor polynomial at c. And so, our Taylor polynomial, it's going to be similar, but it won't be exactly the same. So this will be our p of x. Or we could call this, I guess we'll call it our p of x for a polynomial, okay? Let's say that this is where our a is, okay? So we're trying to find the function's value at a. So this is the exact, so that if I follow it over, that's going to be my f of a. This is going to be my approximation using the Taylor polynomial. This value from here to here is my error. That distance is my error. This over here would be my p of a if I followed that across. And this distance is going to be my Taylor polynomial at a.